Welcome. In this video, we're going to be talking about two different hydration reactions where we're adding water basically across a carbon-carbon double bond, right? Across the pi bond. We're adding an alcohol group and a hydrogen on either carbon of the carbon-carbon double bond. Two completely different reactions. One is known as an acid-catalyzed hydration, so it's acid in the presence of water. Acid-catalyzed hydration, and the other one is known as hydroboration-oxidation. Right, so in the hydroboration-oxidation, so we're going to use methyl cyclohexene, right, to hydration. So what we're adding is water and a hydrogen across a carbon-carbon double bond. But what happens in hydroboration-oxidation is the alcohol group adds to the less substituted position. So if you think about it, that is what we call an anti-Markovnikov. An anti-Markovnikov addition, right? So what we have is really the hydrogen on the more substituted position. But because of the way the mechanism works, that alcohol and the hydrogen add to the same side of that carbon-carbon double bond, or to the same phase that carbon-carbon double bond. Meaning, if that alcohol group, let's say, was on a wedge, there would be a hydrogen right here that's on a wedge as well, right? And this would be on a dash. So it's also what we refer to as a syn addition, right? Remember, we don't draw hydrogens attached to carbons, but if one of the two sides of that carbon-carbon double bond is more substituted, that group and the alcohol group will be opposite, because the hydrogen and the alcohol are on the same phase of that carbon-carbon double bond. So it's what we call a syn addition. Okay, so it's an anti-Markovnikov, and it's a syn addition, right? It's a two-step reaction. Hydroboration is one, oxidation is the other, right? In hydroboration, we're really using borane, right, BH3, and we complex it using THF, tetrahydrofuran, which looks like this, and it really avoids forming a diborane. Right, and in the second step, it's the oxidation. So it's in the presence of hydrogen peroxide under basic conditions. So in the presence of sodium hydroxide, sometimes you'll just see it written as a hydroxide group. Well, in an acid-catalyzed hydration, we'll still use methyl cyclohexene, right? We're still adding. They're both hydration reactions. So in both cases, we're adding water. But in acid-catalyzed hydration, the alcohol group adds to the more substituted position of that carbon-carbon double bond. So it's really a Markovnikov addition. Yeah, you can write it out, Markovnikov addition, right? And it's an acid-catalyzed hydration, so what we have is hydronium ion, right? It's more dilute, so we have more water than an acid. So you could see it written as hydronium ion. You could see it written as H2 sulfuric acid in water, or you could see it written as dilute concentration of sulfuric acid. Okay? Any one of those will apply. So we're going to start with the mechanism of an acid-catalyzed hydration because it's a little simpler and correlates more to what we've seen before than in hydroboration-oxidation. Okay, so you have hydronium ion. And what we have is the pi bond that can act as a nucleophile. It will deprotonate hydronium ion. Okay. And then remember, the hydrogen can add to either carbon of the carbon-carbon double bond, forming a carbocation. So it could either be a tertiary carbocation or a secondary carbocation. Tertiary carbocations are more stable, so the hydrogen adds to the less substituted position of that carbon-carbon double bond. So now our nucleophile is water, right? So water will attack the carbocation, right? This is a carbocation on that carbon. And because it goes through a carbocation, it could attack from the top or the bottom, so you could end up having both enantiomers, and that is true in general when you think about a mechanism that goes through a carbocation, right? So now you have a bond to water, right? It's still connected to both hydrogens. It's water, right? It's positively charged. This pen is great. It's positively charged. So and then the next step is really to deprotonate water, this water. Right, so another water molecule will deprotonate it. Those 2 electrons would go to the oxygen, and we get our final product, so an acid-catalyzed hydration. Okay. I am going to redraw this just to make it more clear. So it formed a bond to water. But now water is positively charged, so we deprotonate it, and those 2 electrons go to oxygen, and we end up with the alcohol group. And again, if it's a chiral center is formed, this is not a chiral center in this case, because if you do the tiebreaker, they'll both end up at the same carbon. If a chiral center was to form, then you get a pair of an enantiomer or a meso compound. Because it goes through a carbocation. So how about hydroboration-oxidation? So we're going to take a look at its mechanism. I'm going to try and use the blue instead. Okay. So right, so that's our reagent, right? What happens is that the pi bond is going to attack the boron, right? And then that hydrogen bond, the boron-hydrogen bond, its electrons are going to go in to form a bond to the more substituted carbon. So think about it, if this was to be a carbocation, then the more stable carbocation is favored. So when the pi bond attacks boron, the hydride, so it's a hydride, it's a hydrogen and 2 electrons that are going to form a bond. But they're forming a bond to the same phase or side of that pi bond. That's why it says syn addition. The hydrogen and the alcohol are going to end up being added to the same side of that carbon-carbon double bond. So it's a syn addition, right? So what we end up getting is now this new bond to boron that still has 2 bonds to the hydrogen atoms. And that same reaction happens twice more, right? It's going to happen twice more. So you're going to repeat 2 more times using both hydrides. So what we end up getting is something that looks like this. Now we have a bond to a boron, a bond, a bond. We have our original reagent. The boron is being added to the less substituted position of it, right? So that's what we end up getting, right? Those are the 3 bonds to the less substituted position of where the carbon-carbon double bond was. So that's hydroboration. And the second step is really the oxidation step. So if you think about it, you have hydrogen peroxide in the presence of an acid. So the acid is going to deprotonate hydrogen peroxide. Okay? And what we end up getting is a deprotonated hydrogen peroxide that will go in and attack the boron. Okay? So we still have the boron, and it has 3 bonds to our substrates, and it formed a bond to the less substituted position of the original carbon-carbon double bond. Okay, but now it has a new bond to this peroxide. Okay, and now that boron is negatively charged, right? So it makes it more susceptible to this bond cleavage. So what happens is that this bond between our substrate and boron will end up being cleaved, but what happens, it goes in and it attacks that oxygen, all right? And those 2 electrons will go to this oxygen instead. And what we end up forming is something that looks like this. So we still have the boron. It still has, so now what left is really an alcohol group, right? Still has its 2 top bonds. Okay, but now we just formed a bond to this oxygen. So we have this bond that now is to an oxygen, and then it's going to be connected to the carbon. So then we end up forming a molecule that looks like this. Okay, and then this step, the oxidation, happens or occurs 3 more times. All right, so you're going to repeat the oxidation step. Okay, so you're going to repeat it 2 more times. And what you get is something that's going to look like this. You don't see it, but turn it up. 1, 2, 3, 4. Okay, so it's going to end up looking something like this. Again, you guys don't see, but it basically, you form 3 of those, right? So then what ends up happening is now that alcohol group can actually attack boron. So you have the alcohol group that will attack, and then one of those 3 attached directly to boron will be our leaving group, right? So that's our leaving group. And then what we end up forming is something that looks like this. So you have the boron. It now just formed a bond to the alcohol group. You have still the 2 bonds to the substrates. Okay, plus what was our leaving group? So you have the oxygen that is negatively charged, and it has formed a bond to our substrate, right? The very last step is water really coming in. Water will protonate it, and then we get our anti-Markovnikov addition. So the very last step is simply water that will protonate it. Those 2 electrons will go to the oxygen, and we get our final product. Right? Which is an anti-Markovnikov hydration, what we call a hydroboration-oxidation mechanism. So there are 2 different reactions that end up adding water across a carbon-carbon double bond. One is a Markovnikov addition, where the alcohol group adds to the more substituted position. One is an anti-Markovnikov addition, where the alcohol group adds to the less substituted position of the carbon-carbon double bond, but it's also a syn addition, and that has to do with the very first step of the reaction, where the pi bond is attacking boron and the hydride is forming a bond at the same time. So it ends up being a syn addition. If you see a group attached on either end, then the group and the alcohol group are anti to one another because the hydrogen and the alcohol are syn to one another. I hope this was helpful. See you next time.